Right now, the device you're listening to this on is, well, it's calculating the exact area of millions of invisible triangles.
Billions of times per second, actually.
Right, billions. And if that calculation stops for even like a fraction of a second, your screen just freezes. The whole digital world goes completely black.
It just crashes. Yeah.
Today, we are taking a deep dive into a piece of math that you probably thought you'd never actually use. We're pulling it out of the classroom and putting it back where it belongs, which is right at the center of the universe.
I mean, it is entirely understandable why people leave this specific math behind. When you're in school staring at, dense brackets, grids of numbers, arbitrary rules for multiplying them.
It feels like torture.
Exactly. It feels completely disconnected from physical reality.
Well,
You memorize the equation just to pass the test. You never realize that it's literally the underlying mechanism for almost everything you touch.
which is exactly why today's deep dive is dedicated to this specialized set of sources we've compiled. It's titled Day 10, Determinants in Engineering and Code. And our mission here is to reveal how the single mathematical concept, the determinant of a matrix, is secretly functioning as, like, the invisible scaffolding of our modern reality. We're going to track it from the flight computers keeping passenger jets from colliding down to the invisible fields hovering over your smartphone screen.
All the way to the hyper-fast processing rendering video games.
Right. Because when you unpack how these matrices actually operate, you realize they are not just abstract numerical exercises.
Wow, not at all. A determinant is essentially a universal translator.
A translator.
Yeah, it takes abstract geometric space and translates it into physical forces, electrical limits, digital boundaries, things that machines can actually comprehend and, more importantly, act upon.
Okay, let's unpack this mechanism, because before we can start flying airplanes with this math, we really need to understand how it maps physical space.
Like the foundation.
Yeah. So our sources start by looking at a pretty fundamental geometric problem, finding the exact bounded area of a 2D triangle. And to do this, you build a 3x3 matrix.
Right.
You take the 3x coordinates of your triangle, stack them in a column. Then you take the 3y coordinates, stack them in the second column. And for the third column, you just put the number 1 all the way down.
Exactly.
You calculate the determinant of that grid, multiply it by a half, and boom, you have your exact spatial area.
And, the structure of that matrix is highly intentional, that column of ones you mentioned.
Yeah.
That's a mathematical necessity to create a square 3x3 grid.
Yeah.
You cannot calculate a determinant unless the matrix is perfectly square.
Oh, because it needs symmetry.
Precisely.
Yeah.
The calculation relies on symmetry to evaluate the space.
Right.
But as you expand into these larger 3x3 matrices, you can't just multiply straight across like you do with smaller ones.
Right, it gets complicated.
You have to break the matrix down into its constituent parts, which involves calculating these things called minors and cofactors.
Okay, and looking at how that calculation works in the source, I was trying to visualize the process of finding a minor.
It can be tricky to picture.
Yeah, but I think it's less like peeling an onion and more like looking at a densely packed city grid.
Oh, I like that.
Right, because if you want to mathematically isolate what's happening at one specific intersection, you have to temporarily block off that entire main avenue and you block off the cross street. You just exclude them.
Yes.
What you are left analyzing is the localized traffic in the remaining neighborhood blocks. That surviving subgrid, that's your minor.
That is an excellent way to conceptualize it. You are systematically blocking out row and column data to evaluate the mathematical weight of one single point within the larger system.
Right.
And then to get the cofactor, you apply a structural rule to that surviving neighborhood. You multiply it by a positive or negative sign, and that's based entirely on its original position in the wider grid.
Which creates that alternating sort of checkerboard pattern of positive and negative values.
Exactly.
Which ensures the final calculation balances out perfectly.
This it does.
But okay, I have to push back on a major focus of this foundational theory.
Okay, go for it.
I understand using this to find an area. But the source places this massive emphasis on what happens when the final result of this matrix calculation is exactly 0.
The collinearity condition.
Yeah, the collinearity condition. But logically, isn't a 0 result just a math failure? Like, if the area of your shape is 0, you didn't measure a shape. You just failed to make a triangle.
That's a fair point.
Why is a 0 result treated as mathematically profound?
Well, it might seem like a failure of geometry at first glance, But in mechanical and systems engineering, 0 is often the most critical answer a system can yield.
Really?
Yeah, you have to think about what a 0 area physically represents in real space. You take the top point of a physical triangle, right,
Okay.
and you slowly push it down toward the base. The enclosed area naturally shrinks.
Great, it's getting flatter.
If that area reaches exactly 0, it means that top point has landed flawlessly on the line connecting the other two base points.
Oh, so the 3 points just form a perfectly straight line.
Precisely. They are collinear.
Mhm.
So in this context, 0 is not nothingness.
It's an alignment.
Yes, 0 is the exact mathematical boundary where a two-dimensional plane collapses into a one-dimensional trajectory. It's the absolute, definitive proof that three objects in a spatial coordinate system are intersecting the exact same line.
Wow. Okay. And if finding out that 3 points form a straight line is mathematically profound, we really need to look at where that is literally a matter of life and death.
Oh, absolutely.
Because the moment we take this collinearity concept out of the textbook and, up into the sky, it becomes the core mechanism for aerospace survival. Let's talk about collision avoidance in modern flight computers.
Yeah, this is where abstract math becomes an active shield. When you have multiple commercial airliners occupying the same general airspace, flight computers aren't just looking at where the planes are right now.
Right, that would be too late.
Exactly. They have to constantly evaluate continuous flight path vectors. Essentially, they're drawing arrows projecting exactly where the planes will be in the next several minutes based on their current speed and heading.
And so the flight computer samples telemetry points from those continuous vectors. It pulls 3 spatial coordinates, builds that exact same 3x3 matrix we just talked about, and continuously runs the determinant calculation.
Over and over.
Right. And what it is looking for is that imaginary triangle between the telemetry points. If the determinant calculation starts shrinking if the area is collapsing towards 0, the flight computer knows those points are aligning.
Because if the determinant hits 0, those independent flight vectors have become perfectly collinear.
They're on the same line.
The planes are occupying the exact same mathematical line in space. A collapsing determinant in a flight computer is the mathematical trigger for an active intercept.
That's terrifying and amazing.
It tells the automated systems and the pilots that a collision is imminent long before human eyes could ever spot the danger through a cockpit window.
It is wild to think that, the blaring pull-up alarm is just the alarm for a collapsing imaginary triangle.
It's exactly what it is.
But the application in aerospace doesn't stop at flight paths, does it? It also governs the physical integrity of the planes themselves.
It does.
Let's look at aerodynamic boundary surfaces. If you imagine a massive, sleek passenger jet, you see smooth, curved metal. But a computer running aerodynamic simulations cannot process a continuous, intricate curve.
No, it has to break it down.
Right. So instead, engineers use finite element analysis. They map the entire outer body of that aircraft as a mesh of thousands and thousands of tiny, completely flat, invisible triangles.
And the reason they rely specifically on triangles for finite element analysis, or FEA, is that a triangle is the simplest possible polygon.
Right.
By definition, any 3 points in space will always create a perfectly flat plane.
Yeah.
You literally cannot bend a triangle without adding a fourth point.
Oh, that makes total sense.
So a complex sweeping curve of an airplane wing is structurally analyzed as an infinite number of microscopic flat planes.
But the computer still has to figure out exactly how much wind resistance, how much aerodynamic force is hitting every single one of those tiny planes.
Yes.
And to do that, it has to know their exact area. So the system runs thousands of determinant matrix calculations simultaneously to instantly find the localized area of every single surface patch.
And the reason calculating that localized area is so vital is that aerodynamic stress is not distributed equally.
No, of course not.
The wind hitting the nose cone exerts a vastly different force than the wind shearing across the trailing edge of a wing. By using determinants to lock down the exact surface area of these microscopic patches, aerospace engineers can precisely scale the localized aerodynamic force vectors.
Okay.
They simulate the exact pressure points where metal might fatigue or fail.
Wow.
It allows them to mathematically stress test a virtual aircraft against, say, hurricane force winds before a single sheet of aluminum is ever even riveted together.
So the exact same math calculating the flight paths to keep the planes apart is also calculating the shear stress keeping the wings attached to the fuselage.
It's all just matrix determinants.
That is unreal. But we've seen how this spatial mapping works for massive metal wings deflecting physical wind. Let's look at what happens when the forces we are dealing with are completely invisible.
Okay, shifting gears.
Yeah, because the exact same spatial logic is required for electromagnetism.
Right. This brings us out of the sky and into the realm of electrical engineering and hardware design. A major focus in this field is something called flux quantification.
Flux quantification.
Yeah. When engineers are building circuits or motors, they have to model magnetic flux. Flux is essentially the total amount of a magnetic field that is actively passing through a given surface area. Usually that's a triangular circuit loop.
Right. And to calculate that flux, engineers don't just need the area of the triangular loop. They desperately need to know its precise orientation in three-dimensional space.
Orientation is everything.
And the mechanism here relies on the cross-product equivalent of our 3x3 determinant, which yields something called the normal vector.
The normal vector, yes.
So to try and visualize this, okay, if I want to figure out how much rain is falling through a tilted skylight, I need to know the area of the glass. But I also have to know exactly what angle the glass is tilted at to calculate how much water actually gets inside.
That's a good way to look at it.
Is that basically how the normal vector works for magnetic flux?
The skyline analogy is a really solid starting point, but we need to refine it slightly to grasp the true complexity of an electromagnetic field.
Okay, refine away.
With a skylight, rain is generally falling downward, but a magnetic field is highly dynamic. It's more like being inside a storm where the rain is violently blowing from every possible direction at once.
Oh, wow. Okay, so the angle matters even more.
Exactly. Because the field is omnidirectional, you need to know exactly which subset of that chaotic energy is passing straight through your circuit loop. That is what the normal vector provides.
I see.
The determinant calculation extracts a vector. Just think of it as an arrow that points perfectly perpendicular, exactly 90 degrees, straight at the surface of your triangular loop.
No, it anchors it.
Yes, it mathematically anchors the loop's orientation relative to the chaos of the magnetic field. Without that strict directional context provided by the determinant, quantifying the flux passing through the system would be impossible.
And this necessity for spatial mapping translates directly to the hardware we all carry around in our pockets, because determinants are also used to map planar sensor arrays.
Yes, touch screens.
Right. We are talking about the capacitive touch fields baked into your smartphone screen.
A smartphone screen is essentially a flat substrate overlaid with an invisible electromagnetic grid. When you tap the glass, your finger disrupts that localized field.
But for the phone's processor to understand where that touch occurred, engineers have to calibrate the spatial coverage metrics of the internal sensor layout.
Correct.
And they use matrix determinants to mathematically define the exact active areas and boundaries of those sensor nodes.
They are mapping the invisible grid so it can react to a physical touch.
But here is where the application goes from brilliant to, like, genuinely mind-bending.
Oh, I know where you're going with this.
Yeah, because the math detects where your thumb hits the glass. But for the phone to react to your touch, for you to scroll or open an app, the device has to instantly render a visual response.
It has to draw the pixels.
Exactly. That brings us to what actually happens when the screen lights up. How does the device actually build the picture?
This is where we cross from hardware into software engineering and computing, specifically graphics rasterization and game engine physics.
Right.
And this domain requires a massive shift in how we think about computational speed.
Okay, let's break down graphics rasterization. Modern GPUs, the graphics chips in your phone, your laptop, or your gaming console, they do not understand curves or complex shapes.
No, they don't.
They process every single 3D object as a collection of triangles. The exact same way finite element analysis breaks down an airplane wing, a GPU breaks down a photorealistic digital race car or a virtual mountain range into a dense mesh of triangles.
But there is a huge translation problem here.
What's the problem?
The GPU is processing a 3D geometric mesh made of triangles. But your actual physical screen is just a flat 2D grid of millions of tiny square pixels.
Oh, right. Triangles versus squares.
Exactly. To bridge that gap, the hardware has to perform triangle rasterization. It has to decide, frame by frame, which specific pixels on your monitor should light up to visually represent the boundaries of those virtual triangles.
And the mechanism it uses to make that decision is profoundly elegant. It uses barycentric coordinates, which rely heavily on, you guessed it, sign determinant calculations.
Sign determinants, yes.
Imagine a single pixel on your screen and a virtual triangle layered over it. The GPU calculates the determinant area formed by the pixel's exact coordinate against the three edges of the triangle.
And it doesn't just look for a number, right?
No, it looks at the positive or negative sign of the result.
Right.
Because the sign of the determinant acts as a spatial toggle. If you calculate the area relative to a boundary line and your point is physically inside the shape, the math yields one sign, let's say positive.
But the moment that point crosses the boundary line to the outside, the spatial orientation flips mathematically, and the result instantly turns negative.
So a positive result means the pixel is inside the triangle, turn it on. A negative result means it's outside, leave it black.
Yes.
It's just a binary inside or outside check based entirely on the math's spatial orientation.
It really is that simple at its core.
But wait, I have to push back here on the sheer computational load of this.
It sounds impossible, right?
Yes. A standard 4K monitor has over 8 million individual pixels. If a video game is running at 60 frames a second, that means the screen is refreshing 60 times every single second.
Yep.
Running a complex matrix calculation for every single pixel against millions of triangles, billions of times a second. Wouldn't the processor literally melt? How does physical hardware actually handle that kind of volume?
It is a staggering volume of calculation, but the secret lies in the simplicity of the math itself. Because the core evaluation is just a rigid, repeating 3x3 determinant, just a fixed sequence of multiplication and subtraction. It does not require deep, complex logical branching.
Oh, so it doesn't have to think very hard.
Exactly. Hardware engineers can physically bake that specific calculation directly into the silicon architecture of the GPU.
Wait, really? Hard-coded into the chip?
Yes. They designed the chip with thousands of microscopic cores dedicated solely to running this one specific matrix operation. So instead of processing one pixel at a time, the GPU processes tens of thousands of them simultaneously in massive parallel bursts.
That is wild.
The hardware is purpose-built to execute this single geometric translation billions of times per second without overheating.
That is incredible. The illusion of a cohesive, moving 3D world on a flat glass screen is just the hyperfast, continuous resolution of determinant areas.
It is.
And the matrix logic governs more than just the visuals, right? It fundamentally dictates the physics of these virtual worlds through collision detection.
Yes. Rendering the shape is only half the battle. If a character in a virtual environment walks into a wall, the game engine has to know to stop them from passing straight through it.
Otherwise, it's not much of a game.
Right. It accomplishes this using bounding volume hierarchies, which are basically simplified, invisible triangular meshes wrapped around the complex digital objects.
Just like the invisible meshes on the airplane wing.
Exactly the same concept. And to check, if two objects collide, say your character swings a digital sword and hits an enemy's shield, the game engine runs blisteringly fast determinant math to check if the coordinates of the sword's hitbox have breached the geometric boundary of the shield's mesh.
It is continuously calculating the spatial relationships, checking if the boundaries intersect.
Constant.
Which means, calculating whether a glowing digital sword connects with a hitbox in a fantasy video game relies on the exact same mathematical foundation as two massive commercial jetliners avoiding a mid-air collision over the Atlantic Ocean.
The symmetry between the disciplines is absolute. In aerospace engineering, the flight computer monitors continuous physical telemetry vectors, waiting to see if the determinant collapses to zero, signaling an intercept that could end in tragedy.
Right.
In a software game engine, the processor monitors digital spatial coordinates, waiting to see if the determinant crosses a mathematical threshold, triggering a programmed intercept that generates like a visual spark effect on your screen.
Wow.
The context couldn't be more different, but the universal truth governing spatial intersection in both realities is the matrix determinant.
I think that perfectly encapsulates the mission of this deep dive. We started with what seemed like a purely academic chore, just organizing numbers into a 3x3 grid to find the bounded area of a triangle.
A seemingly useless exercise.
Yeah. But we watched how blocking out avenues in that grid through minors and cofactors revealed the localized truth of the math. We saw how a zero result wasn't a failure, but the profound boundary between shapes and lines.
And then we watched that simple set of rules scale up. It mapped the continuous flight paths of passenger jets. It broke down sweeping metal fuselages into localized flat planes to scale aerodynamic stress.
It isolated the exact normal vectors needed to pull orientation out of chaotic electromagnetic fields.
And finally, we saw it hard-coded into silicon, processing billions of binary spatial checks a second to render vast interactive virtual realities out of nothing but math and light.
It's just amazing. So the next time you tap a glass touchscreen or watch the wing of an airplane flex against the wind out your window or just navigate a character through a sprawling video game, we really hope you remember the invisible scaffolding.
It's everywhere.
It's all determinant calculated triangles, quietly keeping our modern world intact.
When you trace the mechanisms all the way down, you really stop seeing abstract equations on a chalkboard. You start to recognize the strict, beautiful structural logic that allows complex systems to understand and interact with physical space.
Exactly. And diving into all of these engineering applications leaves you with a genuinely mind-bending thought.
What's that?
If our most advanced supercomputers construct complex, photorealistic virtual worlds entirely out of microscopic, mathematically calculated triangles, constantly evaluating intersection boundaries, well, it really makes you wonder, is there a fundamental pixel or invisible geometric mesh to our own physical reality that the universe is constantly rendering?